Ever wondered what makes a quantum computer so incredibly powerful? Well, it all boils down to this one tiny, kind of mind-bending component, the qubit. So in the next few minutes, we're going to pull back the curtain, demystify this thing, and see why it's poised to completely change technology as we know it.
So let me just start with a question. What if a computer bit could be both a 0 and a 1 at the exact same time? It sounds impossible, right? Like some kind of paradox. But that very idea is the key that unlocks the mind-boggling power of quantum computing. It's what separates it from every computer we use today. Okay, so here's the fundamental difference, right? A classical bit, the kind in your phone or laptop, is basically a light switch. It's either on or it's off, a 1 or a 0. It's locked in. But a qubit, well, a qubit is more like a dimmer switch. It's got this whole range of possibilities between on and off. It can be a little bit of on and a whole lot of off, or vice versa, all at once. And this is where the magic really begins. Now that we've got that basic idea, let's leave that simple on or off world behind us and step into the strange, wonderful, and frankly, much more interesting realm of the qubit.
So what is a qubit officially? The textbook definition says it's the quantum version of a classical bit, the basic unit of quantum information. But that simple definition hides a whole world of complexity and power. It's not really what it is that's so amazing, it's what it can do.
Every superhero has a superpower, right? And the qubits is a real mind bender. It's this quantum trick that lets it be in multiple places, or more accurately, multiple states, all at the same time.
And that superpower has a name, superposition. It means a qubit isn't stuck being just a 0 or just a 1. Instead, it can be a mix of both, existing in this kind of ghostly state of pure potential, right up until the exact moment we look at it or measure it. Now, I know that might sound a little abstract, maybe a little weird, so let's make it more concrete. Let's use a simple analogy. Just imagine you flipped a coin into the air. So, while that coin is spinning, is it heads or tails? Well, it's neither, but it's also kind of both, right? It's just a blur of pure potential. It's only when it lands, the moment it gets measured, that it's forced to pick a side. A qubit in superposition is exactly like that spinning coin. It's a beautiful blend of possibilities right up until we look. And this is how scientists actually write that spinning coin state down on paper. Now, I know it might look a little intimidating, but all it's really saying is that the qubit is some amount of the 0 state plus some amount of the 1 state. Those Greek letters alpha and beta, they just tell you how much of each state is in the mix. That's it. All right, let's take a closer look at those strange symbols. It's the language of quantum mechanics, and while it might look a little complicated, it's actually just a really clever and compact shorthand. This special language is called Dirac notation, or sometimes bracket notation. Just think of it as the sheet music for quantum mechanics. It's the standard way physicists write down these quantum states. Honestly, the main thing to remember is that these symbols are just labels. That symbol there, Ket 0, is really just a fancy way of writing 0, and Ket 1 is a fancy way of writing 1. It's a system for keeping things organized, not some crazy complex math you have to solve. Okay, so we've got the concept and we've got the language. But can we actually visualize a qubit? Is there a way to, see all these possibilities at once? Well, as it turns out, there is. Scientists came up with this really beautiful and elegant way to visualize a qubit, and it's called the block sphere. Think of it like a 3D map of every single possible state a single qubit can be in. So imagine a globe. The North Pole, right at the top, represents the definite 0 state, and the South Pole, all the way at the bottom, is the definite 1 state. For a classical bit, those are the only two options it has, North Pole or South Pole. That's it. So where's our spinning coin? Where's that perfect 50-50 mix of 0 and 1? Well, that lives anywhere on the equator of the sphere. But here's the really cool part. It's not just the poles and the equator. Any point on the entire surface of that sphere is a possible state for the qubit. That's the real power here, an infinite number of possibilities all contained in one tiny particle. So we've got superposition, we've got a way to write it down, we even have a way to visualize it. But so what? Why does any of this actually matter? How does this quantum weirdness translate into real-world computing power? Well, here's how it all connects. Because a qubit can exist in superposition, it can explore many, many possibilities all at once. This amazing ability is called quantum parallelism, and that is the secret sauce.
It's what allows quantum computers to tackle problems that would take even our best classical supercomputers literally billions of years to solve. I mean, the difference in scale is just astronomical. It's not even a fair fight. A classical bit gives you one piece of information at a time. A qubit, with its infinite surface of possibilities, gives you access to a whole universe of information, all at once. Okay, so let's do a quick recap. What are the big things to remember? Qubits use superposition to exist in a blend of states. We use that special language, Dirac notation, to describe them. We can visualize all their possibilities on the Bloch sphere. And all of this together unlocks the incredible power of quantum parallelism. You know, we've really only just scratched the surface of what a single qubit can do. So I'll leave you with this question to chew on. If one qubit is this powerful, what happens when we link thousands or even millions of them together? The possibilities are truly mind-boggling. And that is the incredible promise of quantum computing.